who'll be talking about real-time classification of explosive transients. So,
Sure. All right. Hi, everyone. So my name's Daniel Muthukrishna. I'm a PhD student at the University of Cambridge. So I'll give a very similar talk to what you had before, but a different analysis, looking at the early part of a light curve instead of a full light curve classification. But so we're at this pretty interesting time in astronomy where we have this unprecedented amounts of data becoming available for the first time. Surveys like the LSST will transform the transient universe, where we'll have millions of alerts being produced every single night, which is orders of magnitude more than we've ever had before. And so I think new and novel approaches are really going to be necessary to be able to deal with and process this amount of data. And so to this end, I've developed a new technique which uses deep recurrent neural networks to try to classify transients for the first time as a function of time, and significantly faster than previous approaches, being able to classify tens of thousands of events within just a few seconds. And so I'll get to how we actually do this. But throughout this talk, I'll explain why transients are important and why early classification is particularly significant. And I'll go through how our deep recurrent neural network architecture achieves this, and the tool that we've developed, it's open source, called Rapid, that we've applied to both simulated and real data from the Zwicky Transient facility. So here's an example of a light curve, and this is where we'll end up at the end of this talk, where we'll be able to classify these light curves as a function of time. All right, so transients are important, right? They've really shaped cosmology and astronomy as a whole. Things like type 1a supernovae led to the discovery of the accelerating universe and then dark energy. Recently, the Nobel Prize was won for the detection of gravitational waves, and we've got these neutron star mergers, which are detected in the optical signature as kilonova events. And then these types of supernova and kilonova lead to most of the heavy elements that we have on Earth and the rest of the universe. And so they are significant, and these are very important events to understand and understand more about how the physical mechanism, how they actually operate. All right, but there's a caveat here where the more that we actually learn about the transient universe, the more we learn how mysterious it really is and how little we actually understand about it. So we've got these areas that we kind of understand, like these thermonuclear supernova type 1As, you've got these core collapse supernova, but then there's all these areas like calcium-rich transients, these 0.18 explosions, superluminous supernovae, which we have very few events and we don't fully understand how they operate and what the physical mechanism behind them actually is. So new surveys will observe an unprecedented number of these transients, and we'll want to be able to classify these early so that we can understand how they operate and prioritize follow-up on them. So for example, when we find an object, we often want to get a spectrum of it. When we're getting millions of alerts a night, there's no way of getting a spectrum of all of those alerts. And so we need to be able to prioritize on what type of object we think it is, and also on how early we think we've found it. So for example, in the case of type 1a supernovae, there are two, we kind of understand them, we don't fully understand the progenitor models of them. So is it a white dwarf that's accreting mass from a massive star and then reaching some mass limit and exploding? Or is it two white dwarfs that orbit each other and merge together, reaching some change-of-seeker mass and then exploding? And we don't know which one of these this is. So when we want to follow up 1As, maybe we don't want to follow them up late, but we want to follow them up early so we can figure out more about this progenitor system. All right, so just to explain, what are transients? So usually we look through a telescope, some image of the night sky, and when we compare an image to some sort of difference image at a different point, so a reference image, eventually we'll get some sort of difference where we have some point of brightness slightly brighter than the previous image. And that there here in this example is a supernova. If we take many of these points and observe them over a function of time, their brightness of that object changes, right? And not only does that brightness change, but it changes differently at different wavelengths. We can produce a spectrum, all right? And we can look at different filters and integrate over this spectrum. And that's what we're observing when we observe light curves in different path lengths. So that's the data we kind of have. But how do we actually train? How do we train a classifier to learn about these things? Unfortunately, a comprehensive training set from real data can't really be obtained. Firstly, if we want to do this for LSST, it's not on yet. But if we want to do this for the Zwicky Transient facility, which is currently on, it's been on for a year, but it hasn't nearly observed enough events of different classes. So maybe we have enough 1As to observe, but we certainly don't have enough calcium-rich transients or parent stability supernovae or tidal disruption events to actually even form a good training set. So the question is, how can we do this? And do we deal with representative data sets? Do we create some balanced data set? Do we augment the data? Or can we just use simulations? So in our case, we're using these simulations developed by this recent program called Plastic, this photometric LSST astronomical time series classification challenge. And what they did was they produced this a set of light curves for a challenge that they put out to the community. But more importantly, they produced a simulated set of light curves of a range of different transient models. And these are some of the transient models I've shown here, okay? And they produced this for LSST, but we've repurposed this software and re-simulated it for the observing conditions of the Zwicky transient facility, where we've matched the cadence properties, the seeing, the atmosphere conditions of the telescope at Palomar. And what we can do is we can simulate 12 different transient models, all the way from a range of different supernova events, all the way down to tidal disruption events and different types of kilonova as well. Overall, we simulate 48,000 light curves, and we split these between our 12 different classes. All right, so as you just heard, there are some previous approaches that people have tried to do this. The problem with previous approaches to classification is that they often require us to observe the full light curve before they can provide a classification. They don't really make use of, by doing this, they're actually kind of treating this light curve as an image, right? You look at the entire light curve and you process information on that. And you're not really using information about the sequential information embedded in this. Like, there is time series information that we can employ, and by treating it like an image, you're kind of missing out on some of that. And within that, you're not really focusing on early classification either, right? You're waiting for the entire light curve to finish. And these can often be very slow, and when you're dealing with millions of alerts a night, you want to be fast, okay? So when you're doing feature extraction processes, which will be fine at the end of a survey when you're just looking at through the entire catalog and you just want to classify objects and find all the 1A so you can create some cosmology. But if you want to follow up things every single night, then, and you want to find things early, you need speed, right? So feature extraction is something that you have to be very careful about because it can take several hours to days of computation time depending on the features you choose to extract. For example, extracting periods can be quite slow. And we're also very fortunate to have a data set which involves a lot more classes than previous classification algorithms have had. Okay, so what our different approach is we've created this software called Rapid, which is this real-time automated photometric identification. And the idea here is that as the transient evolves in time, our classification probabilities evolve as well. So you can see at the start, we predict this object as pre-explosion, and then that kind of drops off as we learn more about the light curve and more information is embedded into it, into the classifier. And you can see this green curve, which is type 1A supernova, slowly becomes more and more confident, and eventually we're very, very confident that this is in fact a type 1A supernova. And you can see that it's about very close to where I say the explosion time is that we predict the type 1A supernova actually being the most popular class, or the most dominant class. All right, so how do we actually make this software rapid? Well, this is the architecture. I'm not going to go into all of this. There's a lot going on here, but I'll try to break it down a little bit. So the information we take in is we take in the multi-band photometric information. So we take in R and G bands, fluxes as a function of time. And we take in a little bit of contextual information. I mean, we use the redshift if we have it. We use some sort of extinction or Milky Way reddening as an input as well. And we perform some selection cuts to make sure our training set is a little bit cleaner, like we exclude galactic objects within 15 degrees of the galactic plane. We correct for Milky Way reddening, and if we know the redshift, we correct for time dilation and assume some cosmology and correct for the luminosity as well. Next, so this is perhaps the most important, so how do we actually shape this before it goes into our classifier? And in doing this is a key step is when we're creating labels to feed into our machine learning algorithm, instead of just labeling this as a type 1A supernovae, we label it as a function of time. Okay, so we create two parts of this. So I create something called a pre-explosion phase before this dotted line, where I say the explosion happened, and a transient phase after this dotted line. And that allows us to actually do time-varying classification, where we teach the algorithm what pre-explosion means and teach the algorithm what each of the transient classes. So in this case, it's a supernovae. In other cases, it would be other transients. And so defining these two sets of phases is imperative to our model. All right, and then finally, how does the classifier actually work? So what is our deep and recurrent neural network architecture? And this is it here, all right? So our input layer is the fluxes as a function of time. And so each column is a time step that we're inputting. And we use these GRUs, which is a variant of a recurrent neural network called a gated recurrent unit, which is the most dominant part of our network. We have a bunch of other things going on here, which I'll briefly explain. But where do these actually stem from, right? So these recurrent neural networks really came to fame with things like Amazon Echo, your Apple Siri, when you say OK Google. And when you think about it, the shape of data of someone saying hi Alexa and you triggering your Amazon Echo device is very similar to a supernova, right? You've got, when you're saying someone says hi Alexa, you've got nothing, 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 someone says hi Alexa, and you get this rise in magnitude in different frequencies of sound, right? That's very, very similar to a supernova, where you have nothing, 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 supernova explodes in multiple passbands of light, right? And so we can kind of use the architecture that's used in these Amazon Echo and these trigger word detection algorithms for supernovae. And I think that's a very exciting opportunity. We can employ very similar techniques that have been used previously. But of course, our data is a little bit different. We have multiple classes. It's not just one single thing. We've got a little bit more sparse data. We can't just place a detector and record regularly, so that makes it a little more complicated as well. And so we embed these different things into our algorithm as well. So just to iterate, just a brief note, I'm not going to go into exactly how this algorithm works. We don't have enough time for that, but I will just briefly say neural networks may seem like, we often call this thing a black box because we don't really understand what's going on inside of it. But that doesn't mean that we don't understand a neural network, right? The form of a neural network is actually quite simple, right? Every single node, these might be all your different fluxes at different points, just take on this equation. We have a simple weight and a simple bias that just feed into every other neuron. So every neuron is defined by this, and it's just a linear equation that you're summing over every single input into a neuron. Then you add you might add some function to this, some sort of activation function to bring some nonlinearity into your network, and that allows you to classify nonlinear parts of your network as well, or of your data as well. All right. So what I've shown you is actually a feed-forward neural network. Probably one of the most. It's also fully connected layers. One of the most basic types of neural network, but it's completely one-directional, right? We can't really go backwards in time, and we're not really going through backpropagation either. So I changed this a little bit, where instead of using this feed-forward, where the information just comes from the current flux, we actually re-input the previous state of the network as an input as well. And so this is called backpropagation through time, and that's what a recurrent neural network allows us to do. It allows us to store not only the current input, the current flux, for example, but it allows us to store in the previous input of the state of the network as well. So you can kind of, if we unroll, this is like the typical representation of a recurrent neural network. If we unroll this out, you can kind of imagine these being your different fluxes at different points in time in your light curve. And you kind of imagine your input being a flux at a particular time state, but also your input being the previous state of the network. And this is a representation of the history of your network. Great. And then that gets output into the rest of your network, and hopefully you can get probabilities from that eventually too. So that's basically this recurrent neural network. We can do, each of these time steps is what we're plotting here, and our output probabilities is what we're plotting here. Okay. We put in these, we've got these gated recurrent units. We put in these dropout layers as well, which help us with reducing overfitting and regularization in general. We have batch normalization to speed up our training. We have this softmax layer at the end, so that we can actually, instead of treating this like a regression problem, we change it into a classification problem where we store our values between 0 and 1. All right, and so we can create one of those plots for every single light curve in our test set. And that allows us to create metrics as a function of time. Okay? So you can see that our confusion matrix is evolving with time, and it improves as we get more and more information along all the light curves. And in the late sets, you can kind of interpret this like, 92% at the end of this type 1a supernova were correctly predicted as type 1a supernova. But there is some, we're trying to maximize the error under this curve as well. But there is some degeneracy going on where, calcium-rich transients are often misinterpreted as 1bcs. And although we can't go into the neural network to understand why that's happening, we can kind of plot these things and see, well, when is it getting misclassified? And there's actually a missing curve here, but the G-band here. But you can kind of see that these light curves do look very similar to each other, and so in some sense you can excuse your network for making this kind of mistake. All right, so perhaps more color information will help us in future when LSST turns on. So that's all simulated data, and the question is, can we use simulated data and apply that straight into real data? And so that's what we've done here. So this is actually a little Twitter conversation I had where we did science on Twitter, and I thought that was pretty cool, where James Gilshon posted this object he found on the Zwicky Transient facility, and somebody said it was a galaxy, and he's like, I don't think that's a galaxy, that looks like a TDE to me. And then I posted back, and this is the first object I actually tried on it, and it classified it. Within the 4th epoch, so just over here, you can see that the TDE comes to the most popular class. And so that was pretty exciting that this does actually work on real data. So just finally, we've made this an open source package, it's available, you can pip install it. But ultimately, Rapid allows us to do prioritized follow-up and allows us to do classification as a function of time because of our recurrent neural network. And this is really, really important to do early classification, to understand these things early. We can do it over 12 different classes, and it's very, very fast. We can classify tens or even hundreds of thousands of objects within just a few seconds, which is very important when LSST turns on as well. Thank you.
Time for questions.
Thanks. Do your classes have any prior probabilities attached to them based on the expected proportions of these sorts of objects?
No, so we don't use rates at all. We only use we create a completely balanced data set, and so that means using rates in a neural network is actually a very dangerous thing to do. There's a lot of history that shows a non-representative set into a classified just doesn't work as well as a balanced data set would. And so we don't do that. And you can imagine a case where a real data set would have, a kilonova being 99 times less likely than a type 1a supernovae. And your classifier automatically learns that it can get a 99% accuracy by predicting everything as a 1a. In fact, it learns against predicting kilonovae. And so it's a very dangerous thing to do that, I think.
Not working.
Okay. Hi, great talk. So just simple question. What would be really cool is if you discovered a new transient, and how would your network, handle that if it's seen something it's never seen before? Would it try and pigeonhole it, or would it, how do you handle that?
Yes, that's a great question. So this is a completely supervised learning approach where we have labeled data and we are outputting things that we've seen before. And so, I think they should, we should have, if we want to do anomaly detection, we should have special anomaly detection algorithms that do this. But what would happen if we passed in a weird transient that isn't in this training set, which is very likely? Well, I don't know. And the most likely thing is that it'll distribute the confidence and the probability vector between the classes that most similar to that input. And so perhaps that's even something to look at as well. If you see that your output is actually predicting a TDE and a kilonovae at high probabilities, that might be something that I want to look closer at this object because that's not something I think is physical.
Hi, thanks for your talk. I just had a quick question. It looks like the end goal here is to apply this to LSST data. And a lot of your simulations are like sort of single event unimodal nova type objects, but LSST presumably pick up many types of objects, maybe periodic ones. Have you tried this on them, or?
Sorry, what, many types of objects?
Many types of objects, maybe not single event nova, it could be a periodic object or something like that, but I don't see that in your simulated data set. Have you tried this, or?
So I don't do any, I think you're asking about variables?
Yeah.
Variable objects in general?
Yeah.
So our training set, we don't actually do a variable classifier because in general, it's very easy to just split out variables from transients if you can get out a periodogram of it and you just get out the periods, you can split that out quite easily. And so this is basically just an explosive transient classifier, and so we're not too interested in that. Extending this to LSST isn't too difficult. It's just 6 different pass bands, so you just extend that matrix that you're putting in.
Okay.
But it's quite trivial to move from ZTF to LSST.
But on a related note to that, I saw the plastic data set for these light curves, and they have these big gaps in them, which yours doesn't have either. So
yeah, that's actually true. That's a good point. And so I actually have trained this on the LSST simulations, but I wanted to test this against real data because we have ZTF right now, and so we can actually have a real metric to test how can we go from simulated to real data, and whether a classifier can actually do that. And it does perform reasonably well with LSST, but I haven't done enough metrics to actually check. And I think, obviously there will be things that need to change because the cadence is very different. It's definitely not as good as ZTF is, so, especially per passband cadence. So I don't know yet, that's a future problem. But right now, I think the focus is to see whether we can get this working on ZTF, and then later on extend this to the LSST once we're sure this works.
Thanks.
One last question, and then we'll move on.
It's a related question, so maybe you can be brief. So for ZTF, I assume one of the reasons you're doing so well is because of the time sampling being very good. And so in a blind survey, you're going to catch many more of these rising curves. In LSST, the time sampling is worse, but the color information is much better.
That's right.
So how do you see briefly how those two things play out in terms of predictivity in your algorithm?
Yeah, so that's a good question. It's difficult to say how well color does at the moment because we only have one color in ZTF. And we're doing actually a work at the moment where we're trying to simulate a bunch of different cadences from LSST and just run rapid through all of those and hopefully find classification performance per class as a function of observing properties, as a function of cadence, and as a function of color and different, color per night or color at different nights, and hopefully that'll actually lead to an answer to that question. But it's difficult to know at this point.